Well, let's try a problem from last time. Find all the asymptotes for y equals x divided by 2x plus the absolute value of x plus 1. All right. Now, how do we approach this? Well, the absolute value certainly is going to throw us off. So probably the first thing we should do is let's translate this into a piecewise function and say, what are the real functions we're dealing with without absolute value? All right. So what we can do here is, so I'm going to grab a darker pen. What we can do is say, look, when does absolute value of x plus 1, when does that really matter? So we say, okay, well, it matters whether the inside is positive or negative. So here, I say that really the dividing line is at when x plus 1 equals 0 or at x equals negative 1. So we're going to split this into two parts. So one part will be, suppose x is greater than negative 1. Now, well, we can even say greater than or equal to. Now, in that case, the absolute value doesn't do anything, because x plus 1 will be greater than or equal to 0. And so what we do is we just say, aha, this is x over 2x plus parenthesis x plus 1, also known as x over 3x plus 1. All right, so that's what happens if, say, I'm above negative 1. Now what if I'm below negative 1? So here, if x is less than or equal to negative 1, now when I look at x plus 1, it's below 0. So the absolute value needs to flip the sign. All right, well, that's not so bad. What we do is instead of adding, we'll subtract. So 2x minus x plus 1. Which leads us into x over, then downstairs we'll have 2x minus x, which is a single x minus 1. Okay. We need to define the asymptotes. And there's two types. There's horizontal and vertical. Let's do horizontal. So they tend to be pretty simple. Because for horizontal, we don't even have to look. We know where to search. So whereas with the vertical, we kind of have to figure out where to look. Okay, so for horizontal, well, there's two places to look. And the first one is what happens as you head to infinity. So as we head to infinity, which variation of the function do we need? The top one. Because as we head to infinity, we're going to be bigger than negative 1. Because we think of infinity as sort of getting large in a positive direction. So our function, x over 2x plus absolute value of x plus 1, we can replace it by the simpler function of x over 3x plus 1. And now, this is a really simple function. It's a polynomial over a polynomial. And you can do things like you can slow it down, divide it by 1 over x. Or you can just say, we've done polynomials here, polynomials. It's the largest terms that really determine what goes on. In this case, it's x over 3x. And the coefficients give us that the limit is 1/3. In a similar direction, well, I should say opposite direction, negative infinity. Well, the only thing that changes is now we use the other variation of the function. So it's the limit as x goes to negative infinity of x over x minus 1. And what happens in this case? It goes to 1 over 1, which is 1. So in one direction it goes to 1/3, the other direction goes to 1. So we have two different horizontal asymptotes, depending upon whether you go to positive infinity or negative infinity. All right. Now let's get to the vertical asymptotes. So the vertical asymptotes, let's start here. So if I want a vertical asymptote and I see this nice function over a nice function, I say, well, the only thing that could possibly cause things to go wrong is if there's a 0 downstairs. So we're looking at the denominator. In this case, the 3x plus 1. What could cause the 3x plus 1 to be 0? So 3x plus 1 could be 0 when x equals negative 1/3. So I say, okay, well, what happens? So if you look at the limit as x goes to negative 1/3 of the function x over 3x plus 1, what we'll see is it's tending to negative 1/3 over 0. Now when we see that, a number over 0, that means that some kind of blow up is happening. But now we have to think, well, is it blowing up in a nice way? So we have to be a little bit more careful. So let's suppose we're a little bit more careful because we like to get all the points. So by being a little bit more careful, let's approach it from the two sides. So negative 1/3 from above, negative 1/3 from below. X over 3x plus 1 and x over 3x plus 1. We know that in both cases, we're going to get a negative number on the top over a very small number. And so the only thing I really care about the top is the fact that it's not 0 and that the sign is negative. So the question about what the behavior is, whether it's getting really large positive or really large negative, boils down to what's happening in your denominator. So we have to think a little bit. So suppose I'm a little bit above negative 1/3. And so if you're not comfortable with that, just choose something above negative 1/3, like 0. What's true about your denominator? Is it positive or negative? It's positive. So what we have is the numerator is a negative number, and the denominator is a small positive number. Negative divided by a small positive will produce a huge number of what variety? Is it a big positive huge number or a big negative huge number? Big negative huge number. And so that tells us it's going to blow up and it's going to go towards negative infinity. All right. Well, what happens here? Suppose I'm a little bit below negative 1/3. I don't know. Negative 1. You know, then you can just imagine it moving up. I still have a negative number in the numerator. It's going to become a small number downstairs, but is it a small positive or a small negative? Small negative this time. So what's it going to be? Well, it's going to be a negative over very small negative, which means that the two signs will cancel out, so it's going to be positive. So this is saying that at negative 1/3, you have things blowing up. All right. So, one other case that we could happen. So that's from here. What about here? X over x minus 1. When could that be a problem? When x equals 1. So x minus 1 equals 0 when x equals 1. All right. So if we do the same analysis, here it's a little bit easier. We're trying to understand x over x minus 1. And we say, aha, goes to like 1 over 0. And in the interest of time, I would say, well, if you ran the same thing from the plus side, you would get, well, you get a plus infinity, and from the minus side, you'd get a minus infinity. Now that's pretty quick, and people might object, but in fact, you should object. I claim that something that we did here was wrong, that we did something we shouldn't have done. What work is on here that shouldn't be there? And why not?
1 is not less than or equal to negative 1.
Aha, someone has cracked the code. They said 1. See, look, this has a problem at x equals 1. But do I care about that problem? The answer is no. You see, I only care about the expression x over x minus 1 if the x happens to be below negative 1. So the fact that there's a problem at 1 doesn't matter. We don't see it. Because when x equals 1, it's a totally different piece of the function. So be careful. You know, make sure that what you're doing actually applies to the right part of the function. Now, what about the other part? Now I've made you nervous. It's like, wait, we did the other one too. Well, notice that this problem comes at negative 1/3. Is negative 1/3 above negative 1? Yes. And so that was a true, we did have to have that there. Okay, so we have these two horizontal asymptotes. We have one vertical asymptote which has two different behaviors depending on which side you approach from at -1/3. All right, and that's the answer. Okay, so now on to today's topic. And we'll do a little bit different, a series of questions. And a lot of these are multiple choice. So we're going to do some practice. Okay, practice with properties of limits. So, as an example, given that the limit as x goes to 0 of f of x is 4, and the limit as x goes to 2 of f of x equals 0, what can we conclude about the limit as x goes to 1 of f of x? And there's a couple of different possibilities here. Did you figure it out? Well, you got a 1 in 4 chance. So what do we know? We know something about 0. We know something about 2. Now, the nice thing about 0 and 2 is like 1 is halfway in between. So it seems reasonable if I want to go halfway in between. Well, halfway between 0 and 4 would be 2. In fact, it must be too good to be true. So it's not A. Now, you say, okay, well, that's not good. Well, what was the second thing? Well, maybe it's still nice. You know, we know it converges at 0. We know it converges at 2. It probably converges. The problem is that we don't know what it converges to. Well, we don't even know if it converges. And we don't know if it doesn't converge. And the answer is, it's none of the above. Now, here's the thing to remember about limits. What is this question trying to drive home? What do limits tell us? They tell us about what's happening nearby. So in essence, when we talk about the limit as x goes to 0, and we talk about the limit as x goes to 2, we say, look, I know a little bit about the function. I know it behaves pretty nicely around 0, and it behaves pretty nicely around 2. And when I say around, I mean like really close by. 1 is a very far away. It's a long distance between 1 and 0. It's a long distance between 1 and 2. And so we can't conclude anything other than about 0 and 2. You can create all kinds of strange functions. All right. Don't worry, we get a lot more questions. Suppose you have the following information about the function f of x. In fact, it's a really clean function. You know when you plug in 0.1, you get out 0. You plug in 0.01, you get 0. 0.001, you get 0. 0.0001, you get 0. In fact, it doesn't matter. As long as you plug in any number that looks like 0.00000, lots of zeros, and then a 1, you still get 0. The question is, what must be true? What can we conclude about the limit as x goes to 0 from above of f of x? But let's ask the question. Suppose it did exist. What's true? It's got to be 0. So if the limit exists, then it has to be the case that the limit is going to be 0. Because as we get close, we can get arbitrarily close and still have values to 0. And the only way that's possible is if the limit were 0. Now the question is the first statement true? The answer is we don't know. It might not exist. Do we have any example of a limit which has this kind of property? Where you got closer and closer. You still keep getting 0 when you plug in at nice points like this, but the limit didn't exist. Have we seen anything? Here's a function. If you let f of x, it's a little bit of a variation, sine of pi over x. This function matches the data. You can check. Suppose you plug in 0.1. If you take 1 over 0.1, what does that become? So 1 divided by 0.1 becomes 10. So it would be sine of 10 pi. Well, sine of 10 pi is 0. I don't know, plug in 0.00001. 1 over 0.00001 is 10,000. Plug it in, you get sine of 10,000 pi. Sine of 10,000 pi is still 0. So what happens is that this function sine pi over x matches all this data. But the limit doesn't exist because it's the same kind of thing that we keep drawing over and over again, where it's like you keep getting this infinite up and down. And what's happening is we're sort of sampling, and it just happens that we chose bad samples. We happen to sample at just the wrong points. where it's like, oh, we happen to hit everywhere where the function is crossing that axis, making us think that it's well behaved. So you should always be suspicious about sampled data. It's like, is it really accurate? How do you know? How do you know? All right. How are you doing so far? Getting them all right? 2 for 2? All right, good. Well, I'll see if I can stump you with the next one or two. So, next one. Given that the limit as x goes to a of f of x plus g of x converges, and the limit as x goes to a of f of x minus g of x converges, what must we be able to say about the limit as x goes to a of f of x and the limit as x goes to a of g of x? And there's 3 possibilities. They both converge. It's possible that they don't converge. Or maybe we just don't have enough information to make any conclusions. It turns out it's not C. I'll tell you that much. You do actually have enough information to figure it out. So you either have A or B. So what's A? They both converge, or it's possible that they both do not converge. What do you think? Do they both have to converge, or could there be some weird situation? Now, if you've hung around mathematicians, you probably know there's usually lots of weird stuff going on. So what's the answer? It's A. They both must converge. Now, why? Well, here's the thing, is we know something about limits. And one of the properties we say is we know that sums of limits must converge and differences of limits must converge. So the claim is I can argue that this limit exists. And here's the observation. And this is kind of going to look strange when you see it at first. But then after a while, it'll look strange still. But I'm just going to look at f of x, and I'm going to write it in the following way. F of x is 1/2 of f of x plus g of x plus 1/2 of f of x minus g of x. Now, it's certainly true you can actually check this out, because you get a half x f of x and a half f of x. That's a full f of x. In the meantime, the g of x's cancel out. But now what's true? You see, limits can break up nicely over addition, and constants pull out as long as the parts that you want to take the limits of both exist. We know the limits exist because that was our assumption. So because of properties of limits, this becomes 1/2 of the limit as x goes to a of f of x plus g of x plus 1/2 the limit as x goes to a of f of x minus g of x. And this is good. We're happy with this part. And this is also good. We're happy with this part as well. Whoops. There we go. And therefore, it's a number. It converges. The limit exists. Okay. So here, the idea is, look, if you know limits exist, put them together and you can get new limits. Now let's do something a little bit related. Suppose you're given the following. The limit as x goes to 2 of f of x plus g of x exists. In fact, it turns out it's equal to 5. But the limit as x goes to 2, it does not exist. It does not converge. What can we say about the limit as x goes to 2 of f of x? So there's a couple possibilities. Maybe it goes to 5. Maybe it converges, but we can't say what it converges to. Maybe it doesn't converge. Perhaps this situation could never happen. And maybe we don't have enough information to make any conclusions about what's going on. 5 choices this time. So many possibilities. What could it be? Well, maybe it's that limit as x goes to 2 of f of x equals 5. But it's not. Maybe this situation can never happen. But it can. Maybe we don't have enough information. We do. So now we're down to 2. It converges, but we don't know what it converges to, because that makes sense, right? We know what the f plus g converges. Or maybe it doesn't converge. All right, what do you think? B or C? It is C. The limit does not converge. All right. But we should think about why. Okay, so here's sort of an idea about why this works. Now, oftentimes we can say, look, there's two possibilities for this limit. And we can sort of put it into there's one of two boxes it's in. So each limit, there's two outcomes. They either converge or it doesn't converge, which we'll just put a little no sign. So converge or not converge. And so each limit goes into one of these two boxes. So the question is, okay, which box does it go into? And I want to argue that it goes into this box here. But here's how I can do it. Let's suppose for a second we tried to put it into our first box. So suppose the limit did converge. Now, if I knew that the limit converged, regardless of what it converged to, I can combine it with the fact that that limit converges. So if the limit as x went to 2 of f of x converged, then what would be true is we could say, well, the limit as x went to 2 of g of x, so we're going to do our same trick as before. That's limit as x goes to 2 of f of x plus g of x minus f of x. In other words, I'm adding and subtracting f of x. But now we have two limits. The first limit converges by our assumption. That's the assumption of the problem. The second one says, well, let's for a second suppose that this f of x converged. And therefore, what happens is, if our assumption that this was true worked out, then I could break it up into two limits which each individually converged. And now I say, perfect, that's a number, therefore the limit would have to converge. But what's the one thing we know about this limit as x goes to 2 of g of x? It does not converge. So if I try to put this limit into the converge box, I reach an impossible situation. And therefore, it can't go into that converge box. So that means we have to put it into here. It has to go into the not converge box. So in mathematics, this is what we call proof by contradiction. If you know any 2-year-olds, they might call it proof by You know, it's not going to work that way. And so you have to think a little bit. I like that one. I like that one. Okay. All right. How are you doing so far? 2 more multiple choice problems left. So, given that the limit as x goes to f of a of f of x doesn't converge, so it's a crazy function, doesn't behave well, what can we conclude about the limit as x goes to a of g of f of x? So again, the inside is terrible. So there's a couple possibilities. A, it also does not converge. B, we don't have enough information to make any conclusions about whether or not the limit converges. Or C, this situation can never happen. Here we go. First off, it can happen, so it's not C. All right, so you got a 50-50 shot now. A or B? What do you think? B? B is the right answer. Now, you might say, wait a second, how is it not A? Well, see, the problem is that it might converge. So you might have a function. We can actually make up functions like f of x. Let's just pick our favorite function which doesn't converge. Anyone have a favorite function which doesn't converge? 1 over x? That's great. It's a wonderful function. Now, here, that's perfectly valid. Let's look at g of x, and let's make a very easy function. Pi. It's lunchtime. I'm a little bit hungry. Food's on my mind. But g of x is actually just the following function. It says, whatever you plug in, I'm just going to give you pi back. So plug in 1, out comes pi. Plug in 1,000,000, out comes pi. Plug in, pi, then you get pi back. That seems fair. All right. So what happens in that case is that g of f of x would always be just pi, and then the limit could exist. So the limit could converge. So you could have, the case could be that g of x could somehow fix your problem in some way. So that's why we don't have enough information to assume that it also does not converge, because something could happen. Now you might say, well, could it also still have a problem? Sure. Here's a way you could do it. Instead of having g of x be pi, choose f of x equal 1 over x, and then g of x is just x. Now g of x equals x is a very simple function. It says, whatever you give me, I'm going to give right back to you. So if you compose f of g of x, or sorry, g of f of x, excuse me, then this is simply just 1 over x still. So it still has the same problem. So in some cases it diverges, in some cases it converges, and therefore we don't have enough information. All right. Given that the limit as x goes to 0 from below of x times f of x equals 3, what can we conclude about the limit as x goes to 0 from below of f of x? So there's a couple of possibilities. Maybe it goes to 3. Maybe it goes to infinity. Maybe it goes to negative infinity. Maybe it doesn't converge. Perhaps we don't have enough information. Or perhaps this situation can never happen. Our biggest challenge yet, 6 possible answers. What one will it be? Well, could this situation ever happen? It can. It's not F. Do we have enough information? We do. It's not E. All right. In fact, I'm going to go one step further, and I'm going to tell you that if we allow for, these answers up here, it's not D. It is one of A, B, and C. All right. Could it be A? Yes. Some people are optimists. In principle, yes. It can't be A. Why not? Well, what does x go to? It's going to 0. So if f of x is going to 3, then I'd be going to 0 times 3, which is not very close to 3. So it's not A. All right, 50-50 chance. Is it positive infinity or negative infinity? All right, it's negative infinity. Okay. Now, how do we figure this one out? This one's a little bit you have to think about, but in fact, there's an easy way to think about it, and here it is. Remember what happens with limits. Limits are telling us what happens nearby. So, what it's saying is that if I am close to 0, just a little bit below 0, that this expression, x f of x, is very close to, which we can say with the little squiggle here, approximately 3. So, just below 0, we have that x times f of x is about 3. So that tells us that f of x is about 3 over x. So that's how it's behaving just below 0. F of x, we're not saying that f of x is 3 over x, but we're saying it's very close to it. So if I can understand 3 over x, I can understand f of x. What happens to 3 over x if I approach from below 0 from below? What does it do? It gets a large negative number. So that's why the answer is C. All right. Good. Well, now a little bit of practice, and we'll just work through these. This is not a multiple choice. This is a multi-part problem. These are the kind of problems we like to put on, homeworks or exams. It's like, yeah, there's only 7 problems, each one having 8 parts. So, but let's go through and see if we can figure these out. Okay, so I have the function f of x. So now we're not being given f of x as a piecewise function. We're not giving it as a nice single expression. It's like, here's this picture. Here's data given to us as a nice picture. And we're trying to figure out, let's understand the function f of x by using the picture. So for which values of a, and we're talking between 0 and 4, does the limit not exist? Well, the answer is 1. Now you're probably thinking, is that one value? No. It's x equals 1. So x equals 1 is the only time when our limit doesn't exist. Now, you might say, wait a second, what about 3? Does the limit exist at 3? Yeah, the limit actually exists. It just happens to be that the function doesn't work very nicely. Yeah, but, all right. Oops, I'm getting ahead of myself. Part B. For which values of a does the function have a removable discontinuity? At 3. Now, how do we know it's a removable discontinuity? Limit exists, but the function doesn't match. So if the limit doesn't match the output, that's removable. So the answer, of course, is a equals 3. And how do we fix it? Well, we fix it by redefining the function at a. So in this case, we would say that f of 3, well, what should the value be? 1. Could we fix our problem at 1? No, because it's not a removable discontinuity. The limit has to exist to be removable. What is the limit, in part C, as x goes to 1 from below of 1 over f of x? Or explain why it does not exist. So what happens to 1 over f of x as we go to 1 from below? So here's 1, and from below means from this side. And so we have, this is the graph of f of x. What's happening to 1 over f of x? Well, so the f of x part is doing what? It's getting closer to 0, so what's happening to 1 over f of x? It gets bigger and bigger. So here, we could say that the limit, as x goes to 1 from below of 1 over f of x, is infinity. It blows up. All right. Find the limit as x approaches 3 of f of x. That doesn't sound so bad. What is the limit as x approaches 3 of f of x? 1. Yeah, we kind of did that one already. X approaches 3 of f of x equals 1. Find the limit as x approaches 3 of f of x. Okay. So, what does the function do? F of x as x gets close to 3. What's the answer? Limit as x gets close to 3 of f of x. There's a couple of possibilities. One of them is doesn't exist, but it does. Another thing is it's some number between 0 and 4. Of course, we can't just arbitrarily pick one of them. Is the answer 2? No. Okay, let's not just randomly guess. All right, we know what's happening here. This part, if we think of it as one of our classic onion type situations, we work from the inside. So the f of x, this is getting close to 1. So we say, okay, fantastic. We know that we have f of something getting close to 1. Now the problem is, and this is the reason why it's reasonable to think maybe it doesn't exist, is at 1 we have a problem. The limit doesn't exist. But let's dig a little bit deeper. We know that f of x is getting close to 1, but come back to the picture here. As I'm getting close to 1, how am I getting close to 1? So as I approach 3 in the x direction, how am I approaching 1 in the y direction? I'm coming in from above. So as x gets closer to 3, f of x gets closer to 1 from above. So what's happening is that my input now, my f of x, is getting close to 1 from the positive side. Well, what happens as I get close to 1 from the positive side? I approach 4. So the answer is 4. All right. So what's the limit as x approaches 3 of f of x? What does that approach? Well, I'm getting close to 4. So what do I approach when I approach 4? Well, whatever this turns out to be. Which, eyeballing it, we'll say is 3.25. Looks like about a quarter of the way between 3 and 4. All right. Good. Well, we have time for a nice problem. We have a couple of them here. Let's see. We could do an easy warm-up. Is that? No, too easy. Too easy. We'll save that one for later. Let's do this one. All right. Find the limit as theta goes to pi 6 of 1 minus 2 sine theta over 2 root 3 cosine theta minus 3. Now, what's interesting here, this is a trig limit. We see trig. And it's not if theta goes to 0. Now, if you happen to know sine of pi 6 is a half, which they told us, you'll see the numerator is going towards 0. And if you know that cosine of pi 6 is root 3 halves, then the denominator is also going close to 0. So currently, this limit here is approaching 0 over 0. And when we see 0 over 0, what does that tell us? Yeah, you guys are good. You've been drinking the Kool-Aid. Good for you. All right. So, the question is, what work should we do? What can we do to help us rewrite this expression? I think some people are, one person said the derivative, but we're not doing that yet because we don't know derivatives. Oh, I know, you're going to like, why did you teach us this at the beginning? But no, that's coming on later. Somebody else was saying conjugate. I think conjugate is a reasonable approach. Now, the reason why conjugate is not the most obvious thing is because usually when we think conjugate, we're like, let's get rid of the square root. But really what conjugate says is, let's square stuff. Now, why is squaring stuff good for us? Well, because trig identities, there's this beautiful one that involves squares. Sine squared plus cosine squared equals 1. So if we're like, hey, if I can square stuff, I can pull this identity and pull it and make it in play. So we have two choices for conjugates. So we don't have to do both. We just have to pick one. Do you want to do the conjugate of the top or the conjugate of the bottom? Top? All right. Works for me. So 1 plus 2 sine theta over 1 plus 2 sine theta. So now we're going to do a lot of work here. Don't forget to keep writing the limit again. Until we take the limit, that follows along. Upstairs we'll get 1 minus 4 sine squared theta. Downstairs, don't multiply. That's going to hurt you. Leave it as the two terms. You only multiply the conjugate part on the part where you want the square. The rest, don't multiply it out. Now we say, cool, hey, sine squared theta, that becomes 1 minus cosine squared. Because I can pull out that sine squared plus cosine squared equals 1 over 2 root 3 cosine theta minus 3 times 1 plus 2 sine theta. So if you rewrite the top, well, that becomes limit as theta goes to pi over 6. Let's see, we got 4 cosine squared theta, and then we have 1, and then we have minus 4, which would be minus 3. And that's divided by, of course, everything downstairs. All right. Now, at this point, we might be thinking, well, we're not getting anywhere, but we are. What can we do now? We can factor. We can factor the top, actually. Let's do something not immediately obvious, but let's multiply by 3 upstairs and 3 downstairs. Now, the reason I want to multiply is essentially whenever you have a difference, you can always think of a difference as a difference of squares. So I'm going to make this 3 squared. So if I multiply everything by 3, then it's still 3 squared. So what do I have? I have 12 times cosine squared. Well, that tells us that we can write this as square root of 12 cosine theta minus 3 times square root of 12 cosine theta plus 3. Downstairs, we still have that 2 root 3 cosine theta minus 3. And we have that 1 plus 2 sine theta. And then we have that extra 3 that we added in. Now, what would we like to be true? What we'd like to be true is to have something cancel. It turns out that square root of 12 is 2 square root of 3. That cancels off. So oftentimes when you have a 0 over 0, the real goal is let's cancel some zeros. We just canceled some zeros. Now we do what? Well, we plug in pi 6, cross our fingers, and nice things happen to us because we're good people. Good things happen to good people. All right. Cosine pi 6 is root 3 over 2. 2 times root 3 times square root of 3 over 2 will simplify to be 3 plus 3 more. Downstairs we're going to get 1 plus 1 more times 3. Well, that means we're going to end up with 6 over 6, giving us a final answer of 1. All right, let's try another problem. Limit as x goes to infinity, 4e to the x plus e to the 2x, sine of 3e to the negative x, divided by 3e to the x plus 5 plus 7e to the negative x. Now, probably the weird thing here is this sine of 3e to the negative x, and how do we handle that? Now, there's a basic philosophy that when you see something with sine, we go back and think of the rule. Limit as stuff, this is a technical mathematical term, but limit as stuff going to 0 of sine of stuff divided by stuff, well, that's 1. So that's always in the back of our mind. So if we see 3e to the negative x, we say to ourselves, okay, well, 3e to the negative x, that goes to 0. So we're like, oh, this is like stuff. All right. So here's what we're going to do. We're going to rewrite this to something that's a little bit easier to handle. So limit as x goes towards infinity, the 4e to the x plus e to the 2x, and then we're going to have sine of 3e to the negative x divided by 3e to the negative x. Now, if I put 3e to the negative x here, I should also put it upstairs. 3e to the negative x. And, all right, so that hasn't changed anything there. I've just multiplied by 1. Then we have 3e to the x plus 5 plus 7e to the negative x. Now, we clean up just a little bit more. Well, let's actually start to think what's happening. Now we have that sine stuff over stuff. That goes to 1. Life is good. There we have 4e to the x. That's big. Here we have e to the 2x and e to the negative x. Combined together gives us e to the x, and there's a 3. That's big too. In fact, notice these are both e to the x's. Downstairs, e to the x. That's big. The 5, it's very 5. And that's going to be small. So what we see is we see a big term and a big term. But not only do we see a big term and a big term, they're actually sort of like very similar big terms. So we can write this as the limit as x goes to infinity, 4e to the x plus 3e to the x times this other piece here, sine 3e to the minus x over 3e to the minus x, all divided by 3e to the x plus 5 plus 7e to the negative x. And now we're ready to say, all right, currently it's going to infinity over infinity. Time for us to pump our brakes. And 1 over e to the x, because that e to the x, that's the big term, both in top and the bottom. So we apply our brakes, slowing it down. Not too much, just right. 4e to the x times 1 over e to the x, that's 4. Similarly, e to the x, 1 over e to the x, that's 3. Then sine 3e to the minus x over 3e to the minus x. Downstairs, 3 plus 5 over e to the x plus 7. Now this is really like a 1 over e to the x, so it's like 7 over e to the 2x. All right, let's think about what happens to our pieces here, because we've got a lot of pieces. as we said, here we have our sine of stuff over stuff. And the inside part's going to 0. So the stuff goes to 0. So that part's going to 1. The 5 over e to the x, that's going to go to 0. The 7 over e to the 2x, that's going to go to 0. Because the e to the x, e to the 2x, those are going to be big. So now we say, look, nothing is like blowing up on us. Everything's well behaved. So our answer is going to be, well, upstairs, 4 plus 3, and downstairs, 3 plus 0 plus 0. We can even say it's 4 plus 3 times 1. So our final answer, the one we're going to write down, giving us full credit, 7/3. Nice, nice. So here, kind of the thing is, you see that sign, and you say, okay, let's apply the rule. Sine of stuff over stuff is 1. Write it in that way, and then not so bad. Life is good. So let's do one more. Finish us up. So here's our last one. For today anyways. I'm sure we'll see some more on some exams coming up. Find the limit as x goes to 4 of this crazy looking expression. Sine of x minus 4. Then downstairs you have the square root of x plus 12 minus the square root of 3x plus the square root of 2x plus 8. So it's like a square root and a square root. It's like, wow. All right, first thing to check, plug in 4. Let's just sort of like read it off. 4 minus 4 is 0. Sine of 0 is 0. So right now it's going towards 0 over. Downstairs we get 4 plus 12 is 16. So that would be square root of 16, which is 4, minus, here we go, 8 plus 8 is 16. So that's 4 plus 12 more makes another 16. And square root of 16 is also 4, or it's 0 over 0. Now, that's wonderful news, because that means that we get to do more work. More work. That's right. 0 over 0 means that the fun isn't ending yet. We get to manipulate. Now, what are going to be our two different things to work on? Well, first off, we have to find a way to handle this sine of x minus 4. And we're going to do the same thing as we did before. We say, look, if we have sine of stuff over stuff, and the stuff goes to 0, this goes to 1. So we're going to try to find a way to get an x minus 4 over there. All right, so that's what we're on the lookout for. So that's coming down the road. Next thing is we really got to get rid of these square roots, and we're going to start doing some gentle massaging, rewriting it. So to get rid of square roots, well, we're going to use conjugation. So limit as x goes to 4, sine of x minus 4, and then we're going to multiply by the conjugate. And the conjugate really is about squaring stuff, and so we're going to get rid of these square roots, or at least some of them anyways. All right, so there's the original. Now the conjugate just says change the sign between the two terms. So there's only two terms. So this is the sign that we're changing. Square root of x plus 12 plus square root of 3x plus square root of 2x plus 8. Square root of x plus 12 plus square root of 3x plus square root of 2x plus 8. Good. Now, what happens next? Well, upstairs, don't do anything. Leave it as two terms. So we're not going to multiply it out. So sine of x minus 4, square root of x plus 12, plus the square root of 3x, plus the square root of 2x plus 8. It's going to be whatever it is what it is, and we'll just live with it for now. Downstairs, a minus b, a plus b. So this becomes a squared. Well, that's x plus 12, get rid of the square root, minus b squared. So minus 3x plus square root 2x plus 8. Now, we can rewrite this. That's the limit as x goes to 4, sine x minus 4, square root of x plus 12. You probably are thinking at this point, it's like, this problem isn't so bad, it's just you have to keep writing down. And that's a lot of problems. You have to keep writing down and being careful. You don't want to lose anything. So here, what do we want to do? We want to combine this together. And so because you see a square root, what you really want to do is you want to say, like, okay, I want to get it to, like, something where it's a minus a square root or a plus a square root. So you can do that conjugation again. So x plus 12, subtract 3x. Probably easiest to write that as 12 minus 2x. Subtract square root 2x plus 8. Okay, so we've simply rewritten the denominator, and we've sort of emphasized, a minus a b, where b is a square root. Now at this point we're like, perfect. It worked once. Let's do it again. 12 minus 2x plus square root of 2x plus 8. Now at some point around here you're probably thinking, hey, shouldn't we be checking that maybe now when we plug in 4 it's going to work? And the answer is no, we don't need to check, because nothing has been canceled. You see, only until you get cancellation you can say, okay, I can handle my 0 over 0. Then you say, well, let's see what's left for the other part. No cancellations have occurred yet. So what do we have? Well, upstairs we grow even more. Sine x minus 4, square root x plus 12, plus that square root of 3x, plus square root of 2x, plus 8, times 12 minus 2x, plus square root of 2x, plus 8. Good, that's a plus sign in the middle. All over downstairs. 12 minus 2x squared minus 2x plus 8. Good. That means that downstairs, by doing conjugation and doing it twice, because we had that nested square root, we've been able to rewrite the denominator as a polynomial. That's great news for us. And what would be really great news is if it factored. And we know it's going to factor. In fact, we are 100% sure it's going to factor, or that we've made a mistake, but probably that it's going to factor, because we believe in our ability to just not make too many mistakes. So let's work on the downstairs. So first off, we square that out. That's would be 4x squared minus 48x squared plus 144. Whoops, 48x, sorry. So to negative 2x squared, that's the 4x squared, minus 24x, but there's two of them, that's for the minus 48x, and the 12 squared gets 144. And then we're going to subtract 2x and subtract 8. So we have 4x squared minus 50x, and then plus 144 minus 8 would be plus 136. All right, there you go. Now at this point you might be panicking and thinking, oh my gosh, we have to factor that. But we don't have to panic, because we know a factor. Remember that we're going to 4. So as x went to 4, we were getting 0, and we can still check it's still true. See, 4 squared is 16, times another 4 gives us 64. Add 136, that's 200. Now subtract 200, that's 0. So 4 is a solution. So if 4 is a solution to a polynomial, that means that it has to be a root. So in particular, this has to factor as x minus 4 times something. But now that you know one root and one factor, the other one's free. See, look, whatever this thing is, if I multiply it by x, it has to give 4x squared. So that says that this factor has to be 4x, because I need that 4x squared. This other factor, well, negative 4 times the constant has to be 136, positive 136. So that's got to be a minus. Now, of course, then the question is, well, what's 136 divided by 4? And the answer is 34. Of course it is. Well, 4 times 30 is 120, and then 4 times 4 is another 16. 120 plus 16 is 136. So here's the thing, is we can take this denominator here and write it as x minus 4 times 4x minus 34. Now, with that fact in place, here we're going to make our nice observation. Remember, our sine of stuff over stuff goes to 1 if we have something going to 0. And what do you have? Sine of x minus 4 over x minus 4. This is going to go to 1 because the x minus 4 goes to 0. Well, that means that now I just have to say what happens to everything else. And now we can plug in the 4. So the answer to the limit, let's switch up colors here, is going to be 1 coming from this part right here, the sine x minus 4 over x minus 4, times, all right, downstairs, 4 subtract 34. Oh, sorry, 4 times 4 subtract 34. So 4 times 4 is 16, subtract 34. We'll simplify that in a second. Upstairs, 4 plus 12 is 16, so we get square root of 16, which is 4. And then here, we'll get 8 plus 8 is 16, square root of 16 is 4. This will be 12 plus 4 is 16, square root of 16 is still 4. All right, so that 4 plus 4 is there. Then we come to this one, we're going to get 12 minus 8, well that's 4. And then here, we're going to get 8 plus 8, that's 16, square root of 16 is another 4, 4 plus 4. All right, so there you go. There's our answer. So that's 8 times 8. 16 subtract 34 is negative 18. And they both have 2 in them. So you end up with negative 32, 8 times 4, over 9. Negative 32 ninths. Exactly what you would have thought when you started. Well, maybe not. But you do the work. You do the work, and you see where it goes, and you get the answer. And sometimes it's not exactly the one you thought, but it works. And keep working. It gets easier. The more you do, the better you get. Be careful, be slow, be patient. These problems are not meant to be sprints. You don't get extra credit for doing it quickly. You get credit for doing it well.